PV cell or any type of light irradiance falls on PV cell, it will produce some voltage. It will be able to supply some voltage if some load is connected to that. And PV cell is basically a specific type of PN junction. Specific type of PN junction. I mean, different type of fabrication is there. So it has some different difference from that normal PN junction. It has some similarity and some differences from the normal PN junction. So this is the basic entity or basic unit of any photovoltaic array. Now, as it is a not normal, it's type of PN junction, so it will be able to supply very small voltage. As we know that PN junction, that forward voltage is like that 0.5 to 0.6, 0.7 volts. So it is approximately able to give 0.5 volt, which is not sufficient for any type of practical application. So what we have to do? We have to increase the voltage capacity, voltage supply capacity of this entity. So one cell cannot supply the required voltage. So what we do? The number of PV cells are connected in series to form this module. Actually, in the market, this PV module and this PV panel will be available. This structure, which is a series combination of number of cells, is known as PV module or PV panel, which can be easily bought from the market. Okay, and the number of cells which are used to fabricate this PV module, that will depend upon the requirement. There are different types of different there are different modules with different specification or different voltage rating, different current ratings are there. Okay, now these PV modules of different specifications can be connected into series and parallel combination to form the PV array, which is used or utilized for the PV system, whether it is grid connected PV system or whether it is a standalone PV system. So this rightmost photograph or picture shows a typical photovoltaic array where 4 modules of voltage rating of 20 volts. 20 volt means this 20 volt is related to some that maximum power point voltage, 20 volt rating. And if the 2 modules are connected in series, it will form one string, and 2 such type of similar strings are connected in parallel. So this complete photovoltaic array is obtained. Okay, now the current rating of this photovoltaic array will be equal to IA plus IB, where IA is the current rating of this module and IB is the current rating of this module, these 2 modules. So current rating, the IPV, the PV array current will be the sum of these 2 string currents, and the voltage rating of this photovoltaic array will be 20 plus 20. Okay, in this way we we obtain different type of different photovoltaic array for any PV system with different voltage rating and different current rating. That will depend upon the requirement. Okay, now come to the PV characteristic. The photovoltaic array or photovoltaic cell, or rather you can say photovoltaic module, I mean these 3 will be having similar characteristic because they are combined in series parallel combination. There are 2 type of characteristics which are defined. One is current characteristic, current versus voltage. On x-axis voltage is there, y-axis PV current is there. And another characteristic is power versus voltage characteristic, PV power versus voltage characteristic. Again, x-axis voltage PV voltage, y-axis PV power. So there are different characteristics which are shown here. So these characteristics are shown for different solar irradiance or different solar insolation. Okay, just consider this top one, this. Okay, this is one characteristic for a particular solar irradiance. The amount of solar energy which is falling on light energy which is falling on the surface of the PV module or PV panel. So current versus voltage characteristic. This point shows the short circuit. We are having two output terminal of that PV module or PV array. So if we short circuit those two terminal, external terminal, the voltage will be equal to 0. And if radiance is falling on the surface, okay, the electrons will be dislodged. I mean, holes electrons pairs will be dislodged inside that PV cell, and they are getting path external through external connection, external short circuit. So specific amount of short circuit current will be flowing. Okay, so ISC, short circuit current. Then if the two terminals are open circuited and still radiance is falling on the surface, there will be voltage across those two external terminal of PV array. That is known as open circuit voltage. So the voltage will vary from 0 to open circuit voltage. Okay, and the current will be like this. So now come to the power. Power will be simply multiplication of that current and voltage. So if we multiply ISC to 0, we will be getting this 0 value, and we multiply VOC, open circuit voltage, into 0 current, open circuit current, that is 0, will get 0 power. So the maximum power will occur at some specific point, operating point or operating voltage, that is known as VMPP, voltage or maximum power point. So power characteristic will be like this. There will be one single peak. Okay, then the voltage at which the maximum power is achieved is known as VMPP. The power is Pmax or PMPP, ISC, VSC. So there are four parameters: ISC, VOC, PMPP, VMPP. There are four basic parameters which defines a characteristic of PV array. And mind it, this characteristic, one characteristic, will be at particular solar irradiance or insolation. So one point I would like to mention here, I mean, I have written the solar irradiance and solar insolation. I mean, generally these two are considered to be a same, but these two parameters, irradiance and insolations, are not same. They are similar. So irradiance means power, the watt per meter square, and insolation is the counterpart of the solar counterpart of the normal energy. Okay, energy, watt per meter multiplied by second. So this is the difference. So, but generally we consider, because we are dealing with power as well as energy if the electrical engineering is concerned. So, but there is a basic difference between the radiance and insolation. Now there is a term standard test condition. Standard test condition is a condition at which the specification of any solar PV module is given. Like it would be given that if it is given on the solar panel that 150 watt solar panel. So what is that meaning of 150 watt? That means at S, which is irradiance, if solar irradiance falling on the surface of PV module is 1000 watt per meter square, and the cell temperature is equal to 25 degrees centigrade, then that module will produce 150 watt maximum value. The maximum value PMPP will be 150 watt. Okay, so it is given. So that is standard test condition at which the specification of general specification of solar PV module is given. So what will happen when solar irradiance is decreased? So there is a the characteristic of the solar module or array will depend upon the solar irradiance and cell temperature. Obviously the cell temperature will depend upon the atmospheric condition, ambient temperature. So if solar irradiance is decreased, the ISC will be decreasing in same proportion. So obviously what will happen, the power will be decreased, and when the solar irradiance is decreased, this VOC is slightly decreased. So the power is decreased, the maximum power or overall power characteristic is lower down, and VMPP will also change from the VMPP at standard test condition with solar irradiance or insolation decreases. Okay, the dependency of the characteristic on temperature will be reversed. If temperature is increased, here if irradiance is decreased, this power is decreased. If temperature is decreased, then this power will be decreased, maximum power will be decreased. Okay, it's opposite, inverse. So if I ask that there is no cloud at all, in the no cloud condition, so if one PV module is uh, there installed in Rajasthan and one PV module is installed in say Arunachal Pradesh, so in no cloud condition, for the same irradiance, or obviously irradiance will be same if no cloud condition is there. If we are assuming that uh, same not longitude, latitude, on the same latitude, if Arunachal Pradesh, you just choose one place in northeast and one place in Rajasthan, so where the PV module will give you more power? So the answer will be Arunachal Pradesh, because temperature plays its own role. Temperature is decreased, that means power is increased. Okay, so I'm talking about with the same irradiance condition. Okay, so these characteristic rather I should say these characteristic is the characteristic of PV module or PV array when the irradiance falling on the whole surface is uniform. But there may be the condition when the irradiance falling on the surface of the PV module or array will not be uniform because of some building or some cloud or some trees like this. So this photograph is showing one PV array where some shadow is there. Here shadow is there. So irradiance falling on this upper side and this one is more than the irradiance falling on the shaded version. So this condition is known as partially shaded condition or partial shaded condition. So the characteristic which we have discussed so far will not be same for the same PV array in the condition of partial shading. Okay, so this right photograph or figure shows a typical condition, partial shaded condition for a PV array. PV array, as we have discussed, that will be series parallel combination of modules. These modules are connected in series, and these to form a string, and these strings are connected in parallel to form the complete module. So these dark PV modules represents that shading, more shading. Lighter one is lightly shaded, and this white module is representing that full irradiance. I mean, full. There is no shading on that these PV module. So in this case, under partial shaded condition, the characteristic will be different. How it will be different? Here, normal condition, there is only one peak. Okay, but in partially shaded condition, there will be multiple peak like this. This one, this one, this one. 3 peaks will be there. So if we see this current characteristic of PV array, it will be ladder-like characteristic, ladder-like curve. And if you look at the power characteristic, there will be multiple peak. Okay, this is very simple. This is the characteristic in very simple partially shaded condition, which is being shown in this photograph. But there are condition very severe type of PV partially shaded condition for the PV array. So in that case, the difference between these two peaks will be very small, and multiple peaks, not only 3, 5, 6 peaks may be there. So what happens? Only one peak will be real peak, and these 2 peak will be local peak. So what is our goal? I mean, to operate the PV array at maximum power point, to optimally or utilize it with its full efficiency. So the MPPT algorithm or MPPT scheme is nothing but to find out or track the maximum power point. I mean, to make the PV array operate at the voltage corresponding to this maximum. Okay. Now this slide shows the different version or different schemes for the PV system. So basically, there are grid connected system, not islanded mode connection. So there, why I'm focusing on grid connected system, because in the grid connected system, we have that option to operate this PV array at maximum power point always. Because if we consider the islanded mode or isolated or standalone PV system, where it is not connected to the grid, it is supplying the local load only. So the production, I mean the energy production, the power production of this PV array will depend upon the load only. So if load is not able to absorb the maximum power, so you cannot operate the PV array at maximum power. I mean, it will be conditional. So whatever power you are generating at PV array, that should be absorbed somewhere. So in the islanded mode or standalone mode, the maximum power point operation is conditional. You don't have that option, privilege to operate it at maximum power point always. But in grid connected system, we have the privilege, because whatever power it is producing, it will supply, I mean, the power will be absorbed or consumed by the local home appliance, local load. Here we can connect its local load, and the rest of power which is being produced can be injected into the grid, because grid we can assume it as the infinite bus. Okay, so there are two types of grid connected PV system. Again, where I mean, this PV array will produce DC power. So to connect or to match this voltage to this PV array, we have to have some power converter. So one scheme is, the conventional scheme is two-stage PV system, that is DC to DC converter and DC to AC converter. Okay, inverter conventionally. And but nowadays, as the power level of PV system is increased, we are going to this DC to AC, single stage PV system. This is two-stage PV system, single stage PV system. So DC to AC inverter is directly connected in between the PV array and the grid. Obviously, filter will be there. So there are some advantage of these two-stage system. What is that advantage? The advantage is, I mean, there are multiple control which are associated with any PV system or grid connected PV system. So what are those control? I mean, if grid is being connected to some source, which is PV array here, so synchronization is needed, AC synchronization is needed. So that synchronization control, that is one part. Then we have to fix some voltage here at the DC link in between these two. Okay, because we have to match this voltage to this voltage. Okay, so voltage control is there, then current control is there, because some power which is being produced here, it is to be injected into that grid, and that involves the voltage as well as current. So current controller is needed, and above all, not above all, but along with those controller, MPPT controller is there, which keeps this PV array output, which tries to keep this PV array output voltage equal to the VMPP, the voltage at which the maximum power is produced from the PV. Okay, so these control strategies, I mean, four control strategies, basic four control strategies are there when PV array is connected to the utility grid. So in this two-stage system, there are two power conversion stages. So these control logics or these controllers will be implemented on these two. Like MPPT controller is implemented on this DC to DC converter, and the current and voltage controller will be implemented on this DC to AC inverter. So the control schemes are isolated. So simple control scheme is there with two-stage system. But what is the disadvantage? Disadvantage is associated with the losses, because there are two power conversion stages. So losses will be increased. I mean, losses will be there in both the stages, and combined losses will be high as compared to the single stage PV system. So in the single PV stage system, single stage PV system, only single power conversion stage is there. And if we increase the PV system, PV generation system, okay, what happens? The proportionate loss will be also increased if two-stage systems are used. So losses are decreased, and that becomes very significant if we keep on increasing the generation capacity of PV array. Okay, but the drawback, I mean, we can say drawback or disadvantage, that all the controller will have to be associated on one power stage. So control scheme should be operated in coordinated manner. All the four control schemes should be cooperated in coordinated manner. So the scheme becomes a bit complicated as compared to two-stage system. But this scheme is preferred for high rating PV system. So whatever it be, in both the grid connected PV system, the approach for MPPT controller will be same. Okay. So what MPPT is basically is it is to track the maximum power operating point on the PV characteristic. That means it will try to keep the PV array voltage equal to the maximum power point voltage. Okay. Now most common methods, which is universally accepted, very commonly these methods are used. Perturb and observe incremental conductance. These two methods are basic methods, but they are very commonly accepted because of their simplicities. There are so many MPPT algorithms which have been proposed by the researchers, so many. Okay, but this incremental conductance, specifically incremental conductance, is having its own significance. Still it's having its own significance because of its simplicity. Okay, so controller, MPPT controller, why what this term is for? I mean, by using this MPPT algorithm, it will give reference voltage at the PV array which is to be operated. So reference voltage means this PV controller will generate a reference voltage, which will be ultimately that VMPP, maximum power point, and this reference voltage will be given to voltage controller finally, and finally the processing of that voltage controller and the process of that power conversion unit, power converter, it will try to keep that output of the PV array voltage equal to the reference voltage. Okay. This slide shows a PV panel, a simple PV panel, okay, which is having some irradiance, receiving some irradiance, solar irradiance or light irradiance. Now some load resistance is directly connected to this PV panel, Will it be able to operate at maximum power point? The answer is yes, but there is one condition. Answer is yes, it can be operated at maximum power point if some load resistance is connected to that PV panel directly. The answer is it can be operated at maximum power point, but that is one condition. It is conditional. What is that condition? Only one condition is that when the value of this resistance. So at some irradiance, this PV panel will be having some characteristic, current characteristic, say this characteristic. Current versus voltage characteristic, PV, VPV, IPV and VPV. Okay, now the value, say I'm taking some example, like IMPP is 3.6 here, VMPP is 17.5 volts. I mean, it is wrongly written, but Just assume it's 17.5. This characteristic and VMPP is not, I had to correct it. There is a mistake. So say 17.5. Okay. So consider this point as 17.5. Okay. Now, this resistance will be having its own characteristic, voltage versus current characteristic, and that will be straight line. Now this, if RL, this RL underscore 2 is say 8 ohms, okay, and this resistance, if the value RL is 4.9 ohms, the characteristic is this one, and when RL is 3 ohms, characteristic is this one. Now VMPP by IMPP is equal to 4.9. VMPP, IMPP, the ratio is 4.9. So for RL equal to 4.9, the operating point voltage will be at maximum power point. No, okay. Let me correct it. Yes, it is correct one. VMPP is 17.5, this one. This is VOC basically. 22 volt is VOC. VMPP is correct, 17.5. This is 17.5. IMPP is 3.6, corresponding to this point, 3.6. ISC is some 3.7. So this one is correct. It's not, there is no mistake. I was a bit confused. Okay, so there is one condition for only one value of RL, which is equal to VMPP by IMPP, that is 4.9 omega. Operating point voltage will be at this voltage, which is 17.5. If RL is increased, operating point will shift at the right side of the maximum power point. If RL is decreased, the operating point of PV voltage will shift at the left side of the MPP. Okay. So is it possible to operate the PV panel at maximum power point for any type of RL? Yes, it is possible. And how it is possible? Power conversion unit, power converter, power electronic converter is connected in between. Okay. So this is one example. One example is DC to DC buck converter or boost converter. Anything can be there depending upon the application, depending upon the requirement of the voltage. If you want to reduce this voltage VPV to VL, according to load requirement, the DC to DC buck converter is used, and if requirement of voltage VL is more than this VPV, the boost converter is needed. So any converter can be used. So by using this power electronic converter, we can operate the PV array at maximum power point for the load resistance, which is different from 4.9. See, if it is directly connected, the load resistance has to be 4.9 to operate the PV array or PV module at maximum power point. So VMPP by IMPP should be equal to VPV by IPV. This is the condition for maximum power point operation. That is 4.9. Okay. Now consider this buck converter. Consider this converter as buck converter. So for the buck converter, very simple equations are there. If you are familiar with buck converter, then it's okay. If you are not familiar, very simple equation is there. Like V output is V load. V output by V input is VPV is equal to D. D is the duty ratio. Duty ratio for the switch. There is a switch connected inside that buck converter. There is one switch. Switch means MOSFET or IGBT or whatever switch. So that switch is turned on and off sequentially, properly, not sequentially, in a cyclic manner. So on off. So that on off period will decide that duty ratio. Okay. So V output by V input is D. Now the power input is equal to power output. So VL into IL. VL load voltage, load current is equal to VPV, IPV, the input voltage and input current. So by using this equation, we can find out that IPV is equal to VL IL by VPV, which is equal to VL by VPV into IL. We can write, we can use this equation, V input by V output by V input is equal to D, and we'll find out that IPV can be written in terms of IL, that is D into IL. So VPV by IPV can be written in terms of VL, IL and D. So it is equal to VL by IL divided by D square, or multiplied by D square. This is wrong. The equation is wrong. So we can write the equation for VPV by IPV in terms of load resistance and this duty ratio. So if our load is say 4.9, D should be 1. And if R load is different from 4.9, by changing this duty ratio, we can make this VPV by IPV equal to VMPP by IMPP and make the PV array operate at maximum power point. So in this way, the power electronic converters are used in between the load and PV array to operate it, to give the flexibility, I mean overall control flexibility on the operating point. Okay. So now come to the MPPT methods. We have discussed about two basic methods, that is PSO method and incremental conductance. This is the simplest and the very basic MPPT method, that is pattern observe. The one slide I'm showing it. Here what happens? The name is clear, perturb and observe. So we give perturbation in voltage. We perturb the voltage. Perturb means disturb or change. We give perturbation in the voltage. We perturb the voltage and observe the power. Observe the power, whether the power is increased or decreased. According to the value of power, according to change of power, the perturbation, the direction of perturbation is decided. So if the voltage is increased, that means perturbation is in positive direction. Okay, the voltage is perturbed positively, I mean increment is given to the voltage. ये voltage आपने increment किया, and the power is observed to be more than the previous power. Power is increased, then the direction of the perturbation will be continued. That means in the next iteration, voltage will be increased. If power is still increased, in the next iteration, voltage will be further increased. So the perturbation of the direction of perturbation of the voltage will be continued if observed power is increased in each perturbation. Take number one. Second point is there, that if the power is decreased after perturbation, the direction of perturbation will be changed. So if we start from here and just see, the perturbation is negative, in voltage is decremented, decrement is given, decrease. The power is observed, power is decreased. So power is decreased, that means direction of perturbation is to be changed. So now in the next step, voltage is to be increased. So here increased, power is increased, next perturbation, voltage will be increased, then power is increased, voltage will be again increased, power, the direction of perturbation will be continued till this point. Now at this point, MPP point is reached. Again, I mean it is continuous operation. It is continuous operation to give the perturbation in the voltage. The next point is voltage will be increased here. But what will happen? The power is decreased. So the perturbation, direction of perturbation is changed. So in the next step, voltage is to be decreased here. Okay, the power is increased. From this point to this point, power is increased. So perturbation will be continued, voltage will be decreased. Now at this moment, voltage is decreased, but the power is decreased. So direction will be changed. So again, voltage will be increased. So it will oscillate across that MPP point. Okay. So that is one drawback, basically, that oscillation at a steady state. And obviously incremental conductance will also have this oscillation. And this oscillation can be reduced if we choose the increment or the decrement step size of the voltage to be small. So a smaller size of step change in voltage will give you lesser amount of oscillation, but at the same time, the MPPT process will be slow, because a smaller change, I mean, it will take more time to reach this MPP. Oscillation will be reduced if we are choosing or selecting a smaller step size. Oscillation will be reduced, but MPPT time will be increased. Okay. So oscillation at a steady state at MPPT time will be there, and incremental conductance will be also having the same oscillation. But another drawback with PSO, which is very basic method of the MPPT, it fails in fast changing environmental condition. If the irradiance is changing very rapidly, this PSO method will fail to track that MPP properly. So it can be understood by these two figures or these two curves. Say P2, this P2. This is a present characteristic for the present irradiance, and this A is maximum power point, and as I have discussed that it is continuous process, always the perturbation in voltage will be given. So at maximum power point, if voltage is perturbed, increment is given, so this power B will be there. So if there is no change in the irradiance, I mean if this characteristic remains same, so obviously power is decreased. That means the next step is the voltage will be decremented. This B is less than B A power, so voltage decrement in the voltage will be given. So it will reach to this maximum power point and it will oscillate across that point. But when this voltage increment is given, and at the same moment, if irradiance is increased, and the new characteristic takes place, so according to that voltage, this voltage, power will be corresponding to the C point, which is more than A. So it will be confused, is it? So increment with the power is giving higher, increment with the voltage is giving higher power. So the direction of increment will be same. So in the next step, increment in the voltage will be given. Okay, perturbation will be the same direction. So it will go away from that maximum power point. And at this moment, if again irradiance is increased, so new characteristic will be the again confused. So it will keep on going away from the maximum power point. So it will be confused. So it will fail in fast, rapidly changing environmental condition. But this INC method, which is also considered to be a basic method, is having the solution of this problem. Okay, this fast changing environmental condition problem, because this is based on the slope dP by dV. So this PV characteristic is there. So dP by dV, I mean dP by dV will be positive at left side of this maximum power point, and dP by dV is negative at the right side of the maximum power point. So we calculate this slope. So if slope is positive, obviously increment will be given on the voltage. If slope is negative, decrement will be given to that voltage reference. Okay, but why we call it incremental conductance? We are using this slope dP by dV. Okay, why? Because, let me explain. Because it is tracked by comparing instantaneous conductance to the incremental conductance. What does that mean? If we see this dP by dV, I mean this is equation representing the various condition. Okay, I mean this dP by dV will be 0 at MPP, there is no slope. Then positive at the left side, dP by dV will be more than 0. Then it will be negative at the right side of the maximum power point, left side, right side, dP by dV positive, dP by dV negative. So if we see this dP by dV equation and we expand it, it will be dP by dV is equal to d, P is equal to Vi by dV. So it will be equal to V di by dV plus I. So it will be 0 at MPP because dP by dV is equal to 0. Now it can be represented as di by dV is equal to I is placed here minus I by V. So di by d, what is I by V? I by V is conductance, representing the conductance. Okay, V by I is resistance, I by V is conductance. So this is the present at the moment instantaneous conductance, and di by dV is the incremental conductance. I mean the difference between the two currents and difference between the two voltages, present instant and previous instant. So by using this equation, we decide that increment or decrement in the voltage on the basis of INC method. So if di by, I mean these are calculated always, I mean that's continuous process, continuously calculated, and according to this condition, the increment will be given. So if di by dV is more than minus I by V, that means the operating point is at the left side of the MPP. So voltage is to be incremented. And opposite will take place when di by dV is less than minus I by V. Okay. Come to the partial shaded condition. So these two conditions, these two basic methods, the P&O method and incremental conductance method, both these method will fail if the partial shaded condition is there. So why? Because if it starts from this place, say pattern 2, okay, or just take pattern 1. If operating point is at this one, okay, previously, and now partial shaded condition is there, okay, then what will happen? It will be able to reach at the global maximum power point. This GMPP means global MPP. LMPP means local MPP. There will be one global. It will be able. But what will happen if the operating point is here and we are using this INC method or P&O method? It will not reach, it will not be able to track this global point. It will stick to this point. If previous operating point is at this place, this point, let me use this pointer, yes, this point, and all of a sudden this partial shaded condition is occurred, then it will stick. Obviously P&O and INC will start, I mean, continuous process there. It will incremented, the voltage will be incremented and it will stick to this point and oscillate across this point. It will not reach to this point. So as with this also, if operating point is at this point, it will stick to this much. This operating point is this point, it will stick to this. And if operating point is at this point, luckily, so it will be able to reach that maximum power point. So it is conditional. So sometimes, very rarely, sometimes it may track that global point, power point. And if luckily the condition, previous condition is the favorable condition, okay, otherwise it will not. So there are so many modification has been done in these P&O, INC method, and different types of other strategies have been proposed by researchers, and they are published to track that global maximum power point in partially shaded condition. But they all have some constraints. I'm saying they all have some constraints. Some methods are very fast and able to track global maximum power point, but they have some constraint that if severe partially shaded condition is there, they will fail. So we in our lab have tested these conditions very rigorously. So very advanced type of MPPT algorithm which are developed for tracking the maximum power point in partially shaded condition, they also fails if some severe partially shaded conditions is there. Okay, so what is the solution? So these points, bullet points are there in partially shaded condition. Let me repeat, many local MPPs are there. Common MPPT method failed to reach, yes. So there are many MPPT, modified MPPT have been developed, but they also have some constraint. They also fail in severe type of partial shaded condition or some type of partial shaded condition. So evolutionary algorithm based on artificial intelligence may give the solution, and this particle swarm optimization based MPPT controller, which is based on evolutionary algorithm, gives the solution to track the maximum power point in PV array in very rigorous, very severe partially shaded condition. And one beauty of this PSO based MPPT algorithm is it's very simple. It's very simple as compared to other algorithm proposed to track the MPP in partial shaded condition. It is accurate solution means it tracks the maximum power point very accurately with fast speed. Okay, now come to particle swarm optimization. Very fundamental things I would like to recall or review for PSO. So particle swarm optimization, as the name is clear, Swarm means, the literal meaning of swarm is group or cluster or flock. When we use this term group for birds, we use the word flock. Bird flock means bird group. Okay. So it was, I mean, different types of optimization methods are there. Various methods are there. Many optimization techniques are there. And many of them have been inspired by the behavior of animal or insects or birds. I mean, live things. Okay. So this PSO is also inspired by bird flocking behavior. A group of bird, the behavior of a cluster or group of the bird, and it was proposed by James Kennedy and Russell Eberhard way back in 1995, and it has been utilized for different types of application, particle swarm optimization. So how it has evolved, I mean, this particle swarm optimization. So if we observe the behavior of the cluster or flock of the bird which are searching for food. I mean, generally the animals or insects are in search for the food. So their behavior pattern, I mean, they will show a specific behavior pattern to find out the solution, to find out the best solution. I mean, the best food. Best food means nearest food. The food at the nearest location of the food or best food. So in particle swarm optimization method, each particle represents, I mean, it is counterpart of the birds. Each particle means each bird. And best solution is food for the bird flock, and best solution in PSO optimization method will be according to the application. For example, here it will be the maximum power point voltage. The best solution will be maximum power point voltage. Okay, so PV array is to be operated ultimately at maximum power point voltage. So reference given to the voltage controller by MPPT controller. MPPT controller means MPPT algorithm will be there on some controller, some digital controller. Okay, and that will sense the voltage and current of the PV array. That will be continuously sensing the voltage and current of PV array, and it will be the algorithm, it will do the calculation according to your MPPT algorithm. It will give the voltage reference to the voltage controller, and that voltage controller will try to keep the PV array output voltage equal to the reference voltage given by the MPPT controller. So this is the logic behind that MPPT tracking with the MPPT controller and voltage controller. So best solution for this application is to find out that reference voltage equal to that maximum power point voltage of the PV array. Okay. So how it proceeds? कैसे proceed करता है? How it proceeds? So each bird will be having its own sense, its own best solution, sense of best solution. The bird will move, each bird will move according to its own experience, according to its own sense of that food, best solution, and it will also be depending upon the movement of the bird will also be depending upon the overall sense of the best solution of the overall group. They communicate with each other. So in this way, each bird will move and the whole group will move to find out the same solution. See? So number of, I mean, that is written here in words, text. So it uses the number of agents. There is another word which is used for particle agents that constitute a swarm, that constitute a group, moving around in search space. I mean, there is a search space where the search for solution is occurred. Now each particle in search space adjust is flying. Each bird in search space adjust is flying according to its own flying experience as well as the flying experience of the other particles. So ultimately the individual gain knowledge from other number in the swarm and they combine its own knowledge and the knowledge of the group, and the social experience will give the movement to each bird to find out a single solution that is best solution. So this logic is used for particle swarm optimization method for any application. So if we define this PSO, it can be defined by these two different points, so that each particle or agent behave according to the two simple rules as we have discussed. I mean, they will move towards the best solution by the particle itself. The particle itself will decide it by according to its own experience where how we'll have to move. Okay, and it will also move based on the best solution of the entire group or entire population. So G best is the best solution for the entire group, among the entire group, and P best is the best solution for a particular particle itself. See? And mathematically, this optimization process can be represented by these two equations mathematically. So there are two parameters you have to keep in your mind, that is position of particle and velocity of particle. Position of particle is represented by this SI. I is nothing but the particle. I mean, there will be say n number of particle. So SI is the position of ith particle. There may be n number of particle. I mean, that number of particle will be decided by the user. Okay. So say n number of particle is there. So SI is position of ith particle. So there will be n position for all the n number of particles. Then this lambda I, velocity of the ith particle, which is a step change, I mean, for the movement. And this position and velocity will be for a particular instant or particular iteration. This PSO method, I mean, search process, it will start at some point. All the n particles will start at some point. Initialization, there will be some initialization. Initial position will be given to all the n particles. Initial velocity will be given to all the n particles. Okay, and they will start moving. And this is iterative process. First movement, step size is given to the position. The new position is obtained, sk plus 1. It is expressed by this sk plus 1. K plus 1th instant, at the k plus 1th instant, the position of particle is equal to the previous position plus the velocity for k plus 1th instant, k plus 1th iteration or instant. Okay, so the position will be changing, keep on changing in each iteration for each particle. So n number of particles are there, so n position will be there at each iteration. Now this can be, the velocity can be calculated by this equation. Velocity for k plus 1 for ith particle will be equal to the previous velocity for that ith particle multiplied by some weightage. Some weightage is given, and this weightage, these weightages or these parameters will be calculated when you design your PSO algorithm by iterative process. So plus these parameters C1 R1 multiplied by this. You just look at it. P best I mean, we are calculating the velocity for ith particle. There are n number of particles, so n number of calculation will be there in each iteration. So ith particle. So this factor, this part, P best I minus SIK. What is this? This is nothing but the best solution for ith particle so far. Best solution for the ith particle so far minus the previous position. See? So this factor emphasizes that the movement will be based on the best solution by the particle itself. And this term C2 R2 multiplied by G best minus SIK. Just look at it. G best is the best solution, best position for the whole group, for among all the particles, minus the previous position of the ith particle. So So in this way, velocity is decided. So this velocity will depend upon, the moment will depend upon both best position of the particle itself and best position for the whole group among all the particles. So in this way, the moment will be decided for each particle in each iteration. This K is iteration number, W is inertia. This will be decided by iterating process by the user when you finally design your PSO algorithm for some particular application. These are random variables between 0 and 1. And P best I, we already have discussed. P best I, G best are the solution for the ith particle, best solution for the best position for ith particle so far, and G best is the best position for among all the particles so far. So far means till that particular iteration. Okay. So the moment will be there. So there should be some condition of the moment. You know, you select one particle, say ith particle. Now this position is calculated. Position is calculated. So up to which point it will move, there should be some condition. There should be some different condition apart from these equation, which will decide the moment of the particle. And that condition or that constraint is objective function, which is known as the fitness value evaluation function. So the moment will be given by these equations, but whether the movement will take place or not will be decided by this inequality. For example, here in the MPPT case, position is the voltage. Okay, position is the voltage. There are 3 reference voltages or 4 reference voltages or n number of reference voltages. Okay, that is the position. So for each reference voltage, there is corresponding power. So that power will be used as objective function or fitness value function to decide the moment. For example, if we are at sixth iteration, okay. So at sixth iteration, SIK, K is equal to 6, SIK corresponding to SIK means position of that particle, one particle, ith particle. So position of ith particle is nothing but the reference voltage, which is to be given to the voltage controller. Reference voltage means the voltage, required voltage of that PV array. Okay, so SIK is that voltage. So corresponding to that SIK, the position, that voltage, there will be the power, corresponding power of the PV array that is calculated. See, at sixth iteration. So before sixth iteration, like 1, 2, 3, 4, and 5 iterations are there already there. Okay. The position, what was the best position? What was the best voltage reference till fifth iteration? I mean, how the best position is decided? The position for which the power, the voltage for which the power is maximum. Okay. Now, if for sixth iteration, for this SIK voltage reference, if this power is more than the best position so far, then only this SIK will be given perturbation, increment or decrement. I mean, movement will be there for this kth iteration. Otherwise the ith particle will be fixed to this P best I. Okay. Okay. Now this whole process, these two equations are represented by, in this picture graphically. I mean, SIK minus 1 is the position, previous position. Then it is moved to this position SIK, kth instant, by adding this step, that is velocity for ith particle at kth instant. And from this SIK, the next position will be SIK plus 1 by adding this. This is the velocity for lambda I or k plus 1th instance. This can be calculated by this, and this. These three, this line, and this dashed line are representation of these three terms. Okay. Now come to the PSO for MPPT, how it is implemented for MPPT. If you have idea about the particles form optimization for different application apart from MPPT, and for example, power system people might be familiar, like this PSO method is also used for the optimal scheduling of generators, or optimal location, deciding the optimal location for different distributed generators, or distributed generating resource set in some distribution network. In those applications, if PSO methods are used for optimization purpose, so many particles are used and so many iterations are used. I mean, it's a very complicated process is there. Okay. In those application, in power system application or other type of application. But beauty with PSO in MPPT is it's very simple. How it's very simple? Let me explain it. So as we have already discussed that for MPPT problem, the position for particle, ith particle SI, I mean there will be n number of particles, will be the reference PV voltage. And velocity क्या है? Velocity will be the perturbation in the reference voltage. And objective function is the power corresponding to that position or that voltage. Say n number of particles are there. Okay, so n number of reference voltages will be selected, and according to each position, according to each reference voltage, there will be different power, and corresponding to those powers, the moment will be decided. The moment of each particles will be decided. Each reference will be changed. N number of particles are there, n number of references are there. So n number of references will be changed in each iteration. And finally, these all reference voltages or position of particles, n number of particles, will come to single point, that is VMPP. Got my point? VMPP. The position of all the n particles will become same at final solution, after the movement, after different iteration, after comparison of the power for corresponding or respective reference voltages for different particles. So finally they will reach to single solution, that is VMPP. So position for all n number of particles, that means reference voltage for all n number of particles will be same, that is VMPP. Now I am talking about the simplicity. The beauty of this PSO regarding MPP is that only 3 number of particles, the minimum number of particles which is required for the PSO method, only 3 number of particles will be able to give the accurate and fast solution. That means it will be able to track MPPT accurately, and it will be able to find out the solution to track the MPP even in complicated partially shaded condition. Then the question may be how it is possible, or how you have decided this n to be equal to 3, because in other type of application there are huge number of particles are used. So in those applications, the functions, objective function, I mean there are multi-objective function type of problems are there. So here, one point, that is a single objective function is there. I mean, there are no multiple parameter, only power is there. Only fitness evaluation function means that is power corresponding to the voltage. That is to be checked or observed. Okay. And when we started this PSO for MPPT, we started with a number of particle equal to 17. Actually, we started earlier at the very first we selected the number of particle to be equal to 17. Okay, it gave the solution. It was not very fast because number of particles is very high, 17, and we started reducing it. We kept on reducing, and finally we came up with this solution that with n number of 3, we are getting the same speed of searching MPP with same accurate result. Okay, so n number of 3, the number of particle is very small, 1, then it will be able to search. So if number of particle is very small, so what will happen? It will require very small space in that controller, digital controller, microcontroller, which will be used to implement the MPPT algorithm. Okay, some digital controller is needed to apply that algorithm. And one more point, that it will be using this simple arithmetic equation. It's not very difficult equation. So again, the equation is simple and number of particles are very small. 3 number of particles are. So the simple calculation is required. That's why a simple digital microcontroller will be, simple chip digital microcontroller will be able to utilize this MPPT algorithm based on PSO and give the best solution. So how it will be implemented? Now we are having the idea about the PSO for MPP. So there will be initialization process. So initialization is done for 3 number of particles. So as we have told that 3 particles are there. So position of these 3 particles will be reference voltage. So VPV1, VPV2, VPV3. Okay. So initial position, initial reference voltage, VPV1, VPV2, VPV3. I mean, they are selected in such a manner that they will be covering the whole search space. Whole search space means the possibility of voltage. The voltage which is possible, the PV array voltage which is possible is from 0 to VOC. Is it? So this is the whole search space. So it should cover the whole search space. So what we do, we take VPV1 equal to 60% of VOC, VPV2 equal to 80% of VOC, and VPV3 equal to 85% or 90% of VOC. So initial reference voltage or initial position of 3 particles are there. Now initial velocity can also be given. This initial velocity, that is step change voltage, will be decided by the wisdom of user, and in our experiment here in the lab, we decided it to be 5 volt for all the 3 particles initial. And obviously this step change or velocity will be changing at different iteration as we proceed, but initially we have given 5 volt step change in velocity, change in voltage, that is lambda 1, lambda 2, lambda 3. These are 5 volt, and VPV1, VPV2, VPV3 are equal to 60%, 80%, 85% of VOC to ensure that the position of these particles covers the whole search space. Okay. So these 2 figures shows the tracking of maximum power point by the PSO. This figure shows the tracking of MPP in the case of uniform irradiance. I mean, this characteristic represents the uniform irradiance showing the single peak, that will be the global peak. And this figure shows the power characteristic of PV array under partial shaded condition. It will be having different peaks, this peak, and this peak. And this one is global peak, which is the final best solution, which must be the final best solution. So 3, you can see this point, and this point. This is square, this is star, and this circle, orange circle, green star, and this purple square. These 3 are the particles. I mean the position. This is 85% of the VOC, This is almost 80% of VOC, and this is 60% or 65. I don't remember. It is 60%. 60% of VOC. So it can be different as well, but it gave the optimal solution. So these three initial position, three particles are there. P best initial, obviously. This is the first iteration. So it is the P best. Only we have decided initial position. Now, according to these two equation, the movement will start. This particle will start moving here towards this solution. These two particles will move, and finally they will reach at single solution, single position. The position of all the particles will be this VMPP, the voltage corresponding to this voltage. The case study which we have chosen is, this one. This is a PV system, schematic of the PV system for the case study. We have chosen that 375 kilowatt PV array, huge PV array we have considered for simulation purpose. Utility grid is there. Simple three-phase inverter, two-level voltage source inverter is used. This is filter, low-pass filter to filter out the harmonics produced by this voltage source inverter. There is a transformer. This voltage, utility grid voltage, we have selected to be equal to 11.6 IEEE distribution bus. 12.6 volts of distribution, IEEE standard distribution network. In this 375 kilowatt PV array, this has been formed by using serial parallel combination of standard 150 watt PV module. The specification of this PV module is given like this: 150 watt VMPP 34 volt, IMPP 44 ampere. Okay, now 25 number of this type of PV modules are connected in series to form a string, and 100 number of such strings are connected in parallel to form this overall PV array. So 100 number of PV module means 4.4 multiplied by 100. The ampere, the voltage becomes equal to 440 volt. 25 number of PV modules, such PV module, 150 watt PV module are connected in series to form the string. So string voltage will be what? 34 multiplied by 25, that is 850. Okay, so in this way, we are getting the specification of this 375 kilowatt PV array. Okay. Now the parameters for PSO which has been used. So we have discussed about that inertia weight W, C1, C2 parameter, R1, R2 parameter in this equation. It's W, C1, C2. So these are decided by using MATLAB programming. These are finalized by using MATLAB programming, again by iterative method. Like for example, initially inertia weight was selected to be 0.9. Okay. Then complete PSO algorithm with this omega W is equal to 0.9 was run. Okay. So some time it took. Some specific time for the solution it took. So that time is recorded. Now the decrement to this W 0.9 is given. 0.02 decrement is given. Again, the solution will convert. The whole PSO MPPT methods were run. Okay. So we found that the solution converges. But number of iterations are increased. So decrement in inertia weight is continuously given. The whole system is run with that value of inertia weight. The whole PSO algorithm for MPPT is run, and iteration is counted. So iteration was being decreased as we are decreasing this inertia weight, and finally inertia weight W equal to 0.4. Okay, the minimum number of iteration came out to be there for the proper solution. To say that for each inertia weight, the solution converged but number of iteration was high. Okay, so at finally omega or w equal to 0.4, we got the solution at minimum number of iteration. So we finalized w equal to 0.4, and that minimum number of iteration was 10 iteration. So within 10 iteration, final solution was obtained. That means the PSO was able to track that maximum power point voltage, okay, within 10 iteration. So if we calculate the time corresponding to this 10 iteration, so this 0.02 second was MPPT times sampling time step for each particle. So there are three number of particles. So the complete PSO time step for one iteration for three number of particles, all the three number of particles will be 0.02 multiplied by 3 equal to 0.06 seconds. So one iteration, for the one iteration, the time taken by the system is 0.06 second. So 10 iteration for any type of condition, I'm mentioning it for any type of partial shaded condition, maximum 10 iteration for the maximum 10 iteration. That means 0.06 into 10 iteration, that is 0.6 second. 0.6 second. So MPPT was obtained for 0.6 second for any type of condition, environmental condition. Now I'm showing some results here. So this is the case for uniform irradiance because the characteristic simple, single peaks are there. So here we have considered a case where the irradiance is increasing from 500 watt per meter square to 800 watt per meter square, and the cell temperature is decreasing from 25 degrees centigrade to 15 degrees centigrade. So 500 watt per meter square with 25 degrees centigrade cell temperature, the characteristic is this one. And suppose the irradiance or environmental condition is changed and irradiance becomes 800 watt per meter square and temperature decreased to 15 degrees centigrade. So irradiance is increased, temperature is decreased, so obviously power will be increased. So characteristic will be this one. So here earlier for this condition 500 watt 25 degrees centigrade, the VMPP is 831 volts and corresponding PMPP 187.5 kilowatt. These two values are the VMPP and PMPP. And here in this condition VMPP 880. 831 was the previous VMPP, 880 is the new MPP for this changed environmental condition. And power is 313.5 kilowatt. Earlier the power was 187.5 kilowatt. Now let me show the result for the conventional PSO or incremental conductance. I mean the PSO and incremental conductance both will be giving the similar results in these cases. So P&O and proposed PSO. So here initially the reference voltage for PV array is say 650. Okay. Now at this moment, the MPPT is enabled. So MPPT will be starting at this moment. So MPPT will start. So for P&O, conventional P&O, the step increment will be given to the voltage and it reaches the maximum power point here. I mean, it takes this much time, huge time is there. Okay. And with proposed PSO, within 10 iteration, it reaches the maximum power point, which is half to the time taken by the conventional PSO. Obviously, incremental conductance will be taking the same time. Both are able to track the MPP but time taken by the conventional method is twice the time taken by P&O method. And another thing is that steady state, that is steady state, for conventional PSO method, oscillation will be there across the VMPP. Here there will be no oscillation, almost negligible oscillation, because all the three particles will be having same reference voltage, same solution. So at this point, at this moment, 1.6, the irradiance is changed. So both will be able to track the voltage, but the problem is same. Oscillation will be there for conventional method, and there will be no oscillation for PSO method. Now come to the partially shaded condition. This is one case. I mean, this picture shows that PV array of that 375 kilowatt. I mean, which was selected in our case study. So 1, 2, 3, 4, 5, 6, 25 number of modules are connected in series. This 25 and 100, 1, 2, 3, 4, 5, 25, 25, I mean 100 strings are connected in parallel to formulate this 375 kilowatt array. So it is shown in the figure. I mean, this white portion is getting the full irradiance. Then lighter one, 600 watt per meter square. I mean, this white portion is getting irradiance equal to 1000 watt per meter square. This lighter portion is getting 600 watt per meter square. Then this darker part 500, then more dark 400. So in this way, I mean, the partial shaded condition was generated or emulated in the PV array, the PV array simulator. And this type of characteristic is there for this case of partial shaded condition. So there are many local peaks, this peak, this peak, this peak, this peak, this peak, 1, 2, 3, 4, 5, 6. 6 peaks are there. There is 1 peak, 2 peak, 1 peak, 2, 3, 4, 5. And it can be observed from this figure. I mean, there is a very small difference between these two voltages. Okay, so the global point is this one, that is VMPP 895 volt with 251 kilowatt. And here at this point, 241.5 kilowatt with 720 volts. So this one is global point because it is having maximum power, 251 kilowatt, which is more than 241.5 kilowatt. So 72, it is global point. This is the local maximum power point, and this is global MPP. Now come to the MPPT for proposed PSO and INC, conventional incremental conductance. So say that initial voltage reference, I mean, initially PV array is being operated at 650 volt. 650 volt. So what is the maximum power point voltage global? It is to 894.5 volt. Our goal is to make the PV array operate at 895 volt to extract the maximum power. Okay. Now it will start from this point 650 volt. That means 650 volt somewhere at this point, 650 volt. Initial point is this one. So with conventional INC method, it will start tracking and it has to stuck. There is no other option at this point. Means voltage equal to 270 volt with corresponding P 241.5 volt. And let us see what happens with proposed PSO. Just look at INC. Start from 650 volt and it reaches that 720 and corresponding power. This is PV voltage, corresponding power. This is power representation of power curve, and this is for voltage. Power is 241 kilowatt for 720 volt with INC, conventional INC. With PSO, it starts, definitely it will start from this point and it reaches the maximum power point, global maximum power point, which is 895 volt, corresponding to this 251 kilowatt. power. So in this way, the conventional method fails, where proposed PSO method is able to track the global power point. There are other conditions we have tested. So earlier, I mean, there are two conditions. I mean, the shifting from one environmental condition, one type of partially shaded condition to another type of partially shaded condition, like that. So here also the INC is able to, I mean, INC will fail that to track the global position, where proposed PSO method is able to track the global MPP. Here, the position of global MPP, the difference is there. Here, the global power point is at the rightmost power point here. But in this characteristic, the global power point is this one. See, 729 volt and 860 volt. Two voltages are there for these two peaks. This peak, the power corresponding to this peak is 198, and power corresponding to this voltage is 220. So this one be the global power point. It is not the rightmost power point. Okay, the global power point may be in between somewhere. So it is also able to track this one in the same way. This. So earlier here in this case, earlier the irradiance was uniform irradiance. Earlier it was uniform. The irradiance pattern was changing from uniform to partial shaded condition. So in the uniform irradiance, the VMPP was equal to 850. So INC with INC oscillating across 850 with PSO, the operating voltage is 850 without oscillation at 1.6, T is equal to 1.6. Say irradiance changes. I mean, from uniform irradiance to this type of partially shaded condition. From 850, it has to reach this 729 to track the global power point. From 850, corresponding to the global power point voltage of uniform irradiance, it has to reach this one. See? Now, incremental conductance, this one, red one is incremental conduction. From 850, it is settling to this 864, which is local maximum power point corresponding to this one. This is local one. This one is global, 729. It is stucking 850. It starts from this point. It is stucking at this point with INC. Will start from this point 850 volt. It will stuck to 864 local power point with INC. Whereas in PSO method, it will start, of course, it will start from 850 volt and it will reach to that global power point, that is 729 volt, corresponding to 202 kilowatt. Let's see, starting from this point and reaching this 729 volt. So here is a small comparison table. I mean, for P&O method, INC method, and PSO, particle swarm optimization method. P&O method is slow, as we have already seen. INC method is slow. PSO method is fast as compared to these two. Partial shaded condition tracking is not possible in these two. It will always track the MPP in partial shaded condition. Okay, the tracking speed obviously not applicable, and it is very fast in PSO. The complexity, what about complexity? As we have discussed initially, I have mentioned that P&O, this is very basic algorithm, MPPT algorithm. So this is simplest. INC, because we have to calculate that DI by DV, it is not as simple as P&O, but it is simple. And PSO method, it's also having arithmetic calculation, so it is also simple. So we can conclude our discussion for PSO based MPPT method with these bullet points. So modified or MPPT method or PSO based MPPT method is simple to implement, give accurate and fast tracking, It is suitable to track MPP quickly in changing environmental condition. The oscillation at MPP are almost zero because the solution, the position of all the three particles will be same, that is VMPP. Okay? And we have tested in different types of partially shaded condition. We found that it's suited for all those complicated partial shaded condition where other proposed method for partially shaded condition fails. There are different methods which have been proposed for partially shaded condition specifically. They fail in complicated partial shaded condition. Okay, and we have tested it for, I can say you, like 36 type of partially shaded condition, 36 cases. In all the cases, this PSO method was able to track the MPP efficiently and very fast. And it is found that this PSO method is structurally simple. Arithmetic equations are used. And due to its mathematical simplicity, the control can be computed very rapidly, and thus its implementation is possible with low-cost, simple digital signal processor or signal digital controller. So this is all about the discussion. So you are most welcome to ask questions.
Any question from the participant side?
You're most welcome to ask any question related to whatever we have discussed so far today. Any question? If you are familiar with, if you work in this area, you'll be able to ask question, generate question. And if you are not working in this area, there may be some question which you feel that it is silly question, but it's a good question for me. So if you are in that state of mind, you can ask that type of silly question if you consider it to be silly.
Sir,
but no question is silly question. Yes.
I think, sir, no question from the participant side.
Any participant? I think I tried to cover, the whole scheme. I have tried to discuss the basic of different parts of the system on which the MPPT is to be implemented, and the algorithm, the calculation. I think I tried to cover it all.
Okay, sir.
Participant?
No question from the participant side. Okay, sir. Thank you for the knowledgeable speech. And thank you so much, sir.
Thank you, Vijayji. By the way, I'm not. Can I? No, excuse me. Can you hear me?
Sir, Vijay, sir, not, sir.
Sir?
Yes, sir.
Vijay is there?
Yes, sir.
Okay.
Sir.
So, आपका परिचय आपसे मेरा परिचय नहीं है.
सर राम ईश्वर बैस.
जी?
सर राम ईश्वर बैस.
ओके.
वो सर जो श्री प्रकाश सर सोनकर आपके अंडर में जो पीएचडी कर रहे हैं.
हाँ.
सर वो मेरे क्लासमेट थे सर एमटेक में.
अच्छा, you are from ISM Dhanbad.
Yes, sir.
Okay, so when did you join this Sonbhadra, REC Sonbhadra?
Sir, 8 December 2017.
Acha, 17. I got it. Many of our students, from ITPHU.
Sir, my
pursuing PhD have joined REC.
Yes, sir. Shri Prakash Sonkar.
Shri Prakash, I'm talking about the students who were pursuing PhD from ITPHU. They joined RECs. Different RECs are there, na?
Yes, sir. Yes, sir.
So, thank you.
Okay, sir. Thank
you very much. Vijay, thank you. Okay, so can I leave?
Yes, sir. Yes, sir.
Thank you.
Sir. Dhanyawad, sir.
Thank you.